Now, I will present about introduction of the topic. Thorium is a naturally occurring radioactive element discovered in 1828 and named after Thor, the Norse god of thunder. It is found naturally in the Earth's crust and is considered as potential alternative nuclear fuel for the future energy production. Thorium-232 itself is not directly fissile, which means it cannot easily undergo nuclear fission on its own. However, when it absorbs neutron, it can transform into uranium-233, which is capable of undergoing nuclear fission and releasing large amount of energy. This topic is also related to fusion-fission hybrid system, which combine nuclear fission and nuclear fission technology in one reactor system. In this system, fusion reaction produce high energy neutron that help convert thorium into usable nuclear fuel for fission reaction. Why this topic was chosen? We choose this topic because global energy demand is increasing rapidly due to the industrial development, technology advance, and population growth. As a result, the world needs more efficient and sustainable energy source. At the same time, fossil fuel contribute significantly to environment pollution and climate change. The release of greenhouse gases from coal, oil, and natural gas has encouraged scientists to search for cleaner alternatives that can reduce environmental impact. Thorium is considered a promising option because it is more abundant in nature compared to uranium, making it potential long-term energy source. This topic is highly relevant to the modern physics because it involves important concepts such as nuclear reaction, neutron interaction, radioactive, and advanced energy technology. Methodology to gathering information. To gather information for this presentation, we carry out independent learning using multiple reliable academic and scientific sources. First, we refer to physics textbook and lecture note to understand the basic concept related to the nuclear fission, nuclear fusion, radioactivity, and neutron reaction. These sources help to build a strong foundation before studying more advanced topics. Next, we also use scientific journal and research article to obtain update information about thorium reactor technology and fusion-fission hybrid system. This material provide more detailed explanation and current development in this field. By comparing information from these different reliable sources, I was able to improve our understanding and ensure that the information present is accurate and relevant. Challenge encountered during research and proper solution. During our research, we encountered several challenges. One of the main difficulties was that many scientific articles use highly technical terminology that was difficult to understand at first. In addition, concepts such as neutron breeding, fusion plasma reaction, and thorium fuel cycle require deeper background knowledge in nuclear physics, making the topic more challenging to study independently. Another challenge was that some online sources provide incomplete and conflicting information regarding the efficiency and safety of thorium reactor. To overcome this challenge, we broke difficult concepts into smaller sections for easier understanding. We also use diagram, animation, and education video to visualize nuclear process more clearly. Furthermore, we compare information from multiple reliable sources to verify the accuracy and consistency of the information before including in this presentation.
Let's start with the core concept. When we think of nuclear energy, we usually think of uranium, but thorium-232 is an incredible alternative, but it has catch. It cannot directly undergo fission. It is that we call fertile, not fissile. So, how do we get energy from it? It has It's a transformation process. First, thorium-232 absorbs a neutron. Then, through a series of beta decays, it changes into uranium-230T. This new isotope, uranium-230T, is a highly fissile material. Once we have uranium-230T, it can absorb a neutron and use successful undergo fission to produce massive amount of energy. Now, how does the actual chain reaction sustain itself? Let's look at the fission process. First, the neutron hit the thorium fuel cycle material, and then, as we just discussed, the thorium eventually converts into uranium-233. When that uranium-233 split, it releases energy along with more neutrons. These newly released neutrons then go on to hit more fertile thorium atom and then continuing the chain reaction and providing a continuous supply to clean energy. Now let's move on to law in modern physics. Firstly, we have Albert Einstein's famous law of conservation of mass energy, which is expressed E equal to mc squared. In classical physics, we used to think mass and energy were completely separate. Modern physics proves there are two sides of the same coin, where uranium-2033 undergoes fission. It split into smaller fragment nuclei and neutrons. If you were to weigh the original uranium nucleus and the incoming neutron, and then compare it to the total mass of the product after the split, you would find that some mass has literally vanished. This missing mass is called the mass defect. Where did it go? It was converted entirely into a staggering amount of kinetic and thermal energy, calculated precisely by multiplying that tiny lost mass by the speed of light squared, c squared. Next, this brings us to our second principle, which is nuclear binding energy. This is the energy required to disassemble a nucleus into its individual proton and neutron. If we look at the binding energy per nucleon curve, heavy elements like thorium and uranium have a lower binding energy per nucleon compared to medium-sized elements like iron. This means heavy nuclei are inherently less stable. When a heavy nucleus like uranium-233 split into two lighter, more tightly bound daughter nuclei, they settle into a more stable energy state. The difference in binding energy between the starting atom and the final product is what is liberated as nuclear energy. Finally, how do we trigger this split? We use the neutron-induced fission principle, which is heavy atoms like uranium-233 don't just split randomly on their own very easily. Instead, we introduce a low-energy, slow-moving neutron, often called a thermal neutron. When the uranium-233 nucleus captures this neutron, it briefly becomes uranium-234. This extra neutron puts the nucleus into an highly excited, unstable state. So, the nucleus begins to vibrate, elongates like a drop of liquid stretching out, and then the electrostatic repulsion between the proton overcomes the strong nuclear force holding it together. The nucleus snaps violently, splitting apart and launching the chain reaction we discussed earlier. Next, we move on to the example and mechanism that demonstrate exactly how thorium fuel fusion-fission system operate in practice, and why it holds such a massive advantage over standard energy production. Firstly, energy density comparison. Massive energy output, which when we look at the energy density, thorium completely shifts the scale. It produces millions of times more energy by weight than traditionally fossil fuel like coal or natural gases. Then, small fuel amount. To put this into perspective, a single ton of thorium can produce the same amount of energy as millions of tons of coal. This high energy output from a tiny amount of starting fuel drastically minimizes the physical footprint needed for mining, transporting, and storing energy resources. Secondly, thorium abundance. Which is beyond its energy density, thorium is incredibly abundant. It is roughly 3 to 4 times more plentiful in the Earth's crust than uranium. Because it is widespread globally and often found as a byproduct of other mining operations, it offers a highly secure, reliable, and a long-term fuel supply for generation to come without the geopolitical scarcity issue of conventional nuclear fuel. Thirdly, fusion driver mechanism. Finally, let's look at the core mechanism that makes this hybrid system work, the fusion driver. In a static nuclear reactor, you need a critical mass of self-sustaining fuel to keep the reaction going. In our hybrid system, we use a fusion core to generate a continuous stream of high-energy neutrons. These fast-moving fusion neutrons escape the core and bombard the surrounding subcritical thorium blanket. This constant supply of external neutrons is what triggers the transmutation and sustains the fission reaction safely, and then giving us absolute control over the power cycle.
Next, we move on to the daily life application. First, reliable and clean electricity generation. The fundamental purpose of this technology is to generate electrical power. This ensures a stable, continuous, and low-carbon energy supplies for homes and businesses, meeting the increasing global electricity demand. For instance, India's nuclear power program aims to significantly expand its capacity to meet growing energy needs and achieve net zero emissions by 2070. Second, long-term energy security and independence. Thorium is 3 times as abundant as uranium in the Earth's crust, and its reserves, like those in India, are vast. Utilizing thorium as fuel could provide thousands of years of energy, reducing reliance on finite fossil fuels and potentially unstable foreign energy sources, thus ensuring long-term energy independence and stable energy prices. Is reduce nuclear waste and environmental impact. The thorium fuel cycle generates significantly less long-lived transuranic waste compared to the uranium-plutonium cycle. The waste produced is also easier to manage and store. This translates to a cleaner environment and reduced long-term burden of radioactive waste disposal on future generations. Fourth and the last, industrial process heat applications. High-temperature reactors such as high-temperature gas-cooled reactor, HTGRS, and molten salt reactors, MSRS, can provide high-temperature process heat. This heat can be used for various industrial processes, including the production of chemical products, mineral fertilizers, synthetic natural gas from coal, and in ferrous and non-ferrous metallurgy. This could make industries more efficient and reduce their carbon footprint. 26. Marks the initiation of a sustained nuclear chain reaction and India's official entry into the second stage of its 3-stage nuclear power program. It's designed to use uranium-plutonium mixed oxide fuel and eventually use thorium-232 in its blanket to break uranium-233, which will fuel the 3rd stage of India program. India Nuclear Energy Program is uniquely structured around a 3-stage plan to leverage its vast thorium reserve given by the limitation of uranium. Next advancements is the continued development of Small Modular Reactor (SMRS). India is pouring money and legal support into developing advanced, smaller nuclear reactors with specific designs, including one that could use thorium for hydrogen production. This strategy is a key part of India's plan to meet its growing energy demands, reduce carbon emissions, and tap into its abundant thorium resources for a self-reliant and sustainable energy future. Move on to the controversies. Uranium-232 contamination and handling. The presence of uranium-232, which inevitably rises in the thorium cycle through several neutron reactions, presents a significant challenge. It is a highly radioactive, requiring heavy shielding and remote handling during fuel fabrication and reprocessing, which significantly increases cost and operational complexity. They had material science limitation. Operating at a higher temperature, for example 900 degrees or higher, which offers improved thermal efficiency, requires advanced material for vessels, piping, and pumps such as ceramics or carbon. Current energy generally limits operation to around 650 degrees Celsius only. So the separation process of the fission requires a lot more materials and harder to find.
Assalamualaikum and hi, my name is Alif and I'll be talking about the potential carriers in thorium energy system. So first we have the nuclear reactor physicists who act as the architect. Their role is to design the reactor core and ensuring the system safely breeds thorium into usable fuel. And next is the material engineer. They are responsible for researching specialized radiation resistance material, a material that can survive extreme heat and corrosive environment inside the reactor core. And next is the computational scientists. They stimulate multi-physics modeling, allowing us to see how heat, pressure and radiations interact simultaneously and in a virtual space. And next is the nuclear chemical engineer. They design the system that processes thorium and uranium fuel. And next is the plasma physicist. They manage and stabilize the high energy fusion reactions. They use a powerful magnetic field to trap 100 million degree plasma, which acts as the vital neutron factory fueling our thorium body. The required skills and development plan. First is looking at the technical skills. There must be a deep mastery of nuclear reactor and physics theory to understand complex principles. This foundation is built through advanced university coursework with the long-term goal of conducting dedicated research thesis on thorium neutron kinetics. Second is the radiation safety and protection, which requires a precise practical knowledge of shielding design, dose limits and exposure reduction. This experience needed include a formal laboratory safety training and simulations. So for the soft skill, first is the safety first mindset, which means prioritizing the environment and strictly following global safety rules. This mindset is we can build this mindset by deeply studying past nuclear safety case studies, with the ultimate goal of aligning all engineering design with the international safety standards like the IAEA protocols. And the second is communication, the ability to work closely as a team and share a complex data in actionable way. So this is developed through peer reviews and group projects collaborations. And last is the analytical reasoning, which is the ability to compare and contrast different information sources to resolve complex challenges. This is practiced by troubleshooting the unexpected error in a digital twin simulations, with the goal of learning how to solve entirely new reactor engineering problems as they arise. So that's all from me. Thank you.
Now, let's move on to my part. First, focusing on thorium technology offers massive carrier potential because thorium reactors operate differently than traditional uranium plants. It creates new pathways in high-tech reactor design. Furthermore, as countries look for more alternative, expertise in this area is highly valuable for global energy policy, planning, and regulatory framework. Second, this field demands and enable advanced skill mastery. Working with modern nuclear system require proficiency in specialist tools like neutronics modeling, which simulate how neutrons behave inside a reactor core. Finally, this field ensures continuous professional growth. The technology is evolving rapidly, particularly with concepts like fusion-fission hybrid system, where a fusion core generates neutrons to breed thorium fuel. Staying engaged with thorium research keeps scientists at the absolute forefront of the clean energy revolution. Next, on this slide, we focus on the challenges and strategies of building a fusion-fission hybrid reactor, which works by wrapping a central fusion plasma core with a thorium blanket to generate clean energy. The major technical complexity here is twofold. First, it is incredibly difficult to keep a fusion core completely stable while it interacts with the dense surrounding blanket. Second, the high-energy neutron shooting out of the core constantly smash into the reactor walls, causing rapid material degradation and wear and tear. So, to solve these engineering hurdles, our strategy is to collaborate with international research labs to design stronger radiation-resistant material and work alongside the IAEA to create specialized global safety certification for this next-generation system. Next, regulatory batteries. This slide looks at the legal and rulemaking problems of running a nuclear system, which involve moving fuel through a cycle, from fresh fuel, pebbles, and molten salt to a reprocessing plant, and finally to deep underground disposal. The big issue here is that our current international nuclear laws are old and strict. They were writing only for traditional nuclear plants, leaving huge policy gaps because they don't know how to handle this new hybrid system. To fix this, our strategy is to work directly with global nuclear watchdog to update and create modern safety rules so this hybrid reactor can legally and safely be built.